In this video today, we are going to take a look at finding the area between curves. There's three different topics that we'll look at here, but they're all basically done the same way. We're going to find area between curves expressed as functions of x, functions of y, and curves that intersect at more than one point. So let's start here by looking at a general graph of what this might look like here. So this is an area between curves that we're trying to find here, okay? We know how to find the area under the blue graph. We know how to find the area under the red graph. And what I'm trying to show here is if we take the area under the blue graph and subtract the area under the red graph, we would get what's left in between there, which is that pink area right there. So basically, to sum up, what we're going to want to do here is we're going to subtract areas between two functions. Okay, so here's our first theorem here. Area of a region between two curves. If f and g are both continuous on the interval, and g is less than or equal to f on the entire interval, then the area of the region bounded by the graphs and the vertical lines x equals a and x equals b is given by this formula right here. What's important to note here is that f and g are two different functions. F is a function that is on top. G is a function that's on bottom. If you do it in the exact opposite way, you'll get the right answer, but it'll be negative. Okay, so we always want to do top minus bottom when we're talking about functions in terms of x. Let's take a look at our first problem here. Find the area bounded by the region find the area of the region bounded by the graphs of y equals x squared plus 2, y equals negative x, x equals 0, and 1. Sketch the graph and show you the region. All right, so first of all, y equals x squared plus 2 is just a parabola. It's going to look like this. And then the graph y equals negative x is a line. Looks like this. X equals 0. And x equals 1. So the region that we're trying to find here is this region that I'm coloring in here in this light blue color. That's the region we're trying to find. Okay, so our integral here is going to be area equals the integral from 0 to 1, because those are our x bounds, of f minus g, top function minus lower function. Top function here is x squared plus 2 minus the lower function here. The lower function here is negative x. All in big brackets or big parentheses, dx. Okay, before we take the antiderivative, let's just simplify this a little bit. So it's x squared plus x plus 2 dx. And now we can take our antiderivative. So it's 1/3 x cubed plus 1/2 x squared plus 2x from 0 to 1. If you put 1 in there, you get 1/3 plus 1/2 plus 2. Minus, if you put 0 in there, you get 0. So our answer is 1/3 plus 1/2 plus 2, which is going to be 2/6 plus 3/6 plus 6/6. If we add that all together, let's see, so 2/6, 3/6, 12/6, that would be 17/6. I think I said the first thing wrong. Be 2/6 plus 3/6 plus 12/6, which would be 17/6, or close to 3, almost 3, as our area. Example 2. I already got the graphs drawn for us here. So the region we're trying to find is this region right here. And again, we want to do our integral from intersection point to intersection point. So we have the graphs. It's pretty obvious if you look at the graphs where they're at. But let's say it's not that obvious. To find the intersection points, all you want to do is set your two graphs equal to each other and see where they intersect. So this would be a nice, easy factoring problem. So it'll be x minus 2, x plus 2, x minus 1. So our intersection points are x equals -2 and x equals 1. So our bounds are going to be area equals negative 2 to 1 of top function minus bottom function. The top function is our parabola, so 2 minus x squared. The bottom function is our line, so x dx. So our area then is negative 2 to 1 of 2 minus x squared minus x dx. So 2x minus 1/3 x cubed minus 1/2 x squared from negative 2 to 1. If we put 1 in there, we get 2 minus 1/3 minus 1/2 minus, if we put negative 2 in there, we get negative 4 plus 8/3. Let's see, 4 over negative 2 would be minus 2. So doing some simplifying there, 2 plus 4 plus 2 is 8. Negative 1/3 minus 8/3 is negative 9/3, which is negative 3, and then minus 1/2. So that would be 5 minus 1/2, which is 4.5, or 9/2. Example 3, a region lying between two intersecting graphs. So here we are again. It says to find the area of one of the regions. So sine and cosine, there's infinitely many regions between them. We just want to find the area of one of them. You can use that one, or you can do this one over here. It doesn't matter. I'm going to do this one here. So I do that one. First of all, our bounds are going to be where sine and cosine intersect. Sine and cosine are the same when x is equal to pi over 4. That would be that point right there. And maybe this is not the best region to do. Let's do this region over here so we can keep our bounds positive. And they're also the same when it's 5 pi over 4, and x is 5 pi over 4. You could do the other one too, just we have a negative bound there, which can be confusing sometimes. So now our area is going to be the integral from pi over 4 to 5 pi over 4. Which function's on top? The red function is in that region. So in that region, sine is on top. So it's going to be sine minus cosine dx. So our area then would be negative cosine minus sine from pi over 4 to 5 pi over 4. So negative cosine 5 pi over 4, that's negative root 2 over 2, minus sine of 5 pi over 4, so that's minus negative root 2 over 2, minus negative cosine pi over 4, so that's negative root 2 over 2, minus sine pi over 4, so minus root 2 over 2. So we have root 2 over 2 plus root 2 over 2 plus root 2 over 2 plus root 2 over 2. So we have 4 root 2 over 2, which is 2 root 2. All right, what if we want to integrate with respect to y? Well, first of all, we never want to do this. This isn't something that we would choose to do unless it makes it easier on us. Okay, so integrating with respect to y, sometimes the boundaries of a region are most easily described as functions of y rather than functions of x. We can use approximating rectangles that are horizontal rather than vertical, and the resulting basic formula has y instead of x. So instead of using what we were doing before, just to go back to these first couple problems, we've been finding all these little rectangles of this shape and just moving them left and right and finding all the areas I'm adding up. So again, here. And again, here. So that's why we call these dx problems, because we're moving the rectangle left and right on the x-axis. But in problems like this, we have these kind of rectangles, which we would move up and down to fill out the shape on the y-axis. So these are called dy problems. For regions like these, we want to use the area from C to D, f of y minus g of y dy to find the area. F of y is no longer the function on top, it's the function furthest to the right. All right, so here's our first one. We can see the region here that we're trying to find the area of. And one of our little rectangles would look like that. And move that up and down to find all the area added together. So let's start by finding our bounds. Set 3 minus y squared equal to y plus 1. And our bounds would be y equals -2 and y equals 1. Y equals -2 and y equals 1. All right, and then our area is going to be the integral from -2 to 1 of the function furthest to the right, which is 3 minus y squared, minus the function furthest to the left, which is y plus 1 dy. And obviously we can do some cleaning up on that, so we don't have to integrate every part there. So it'd be 3 minus y squared minus y minus 1. And we can even clean up a little bit more and make it -y squared minus y plus 2. Now we can take our integral, so -1/3 y cubed minus 1/2 y squared plus 2y from -2 to 1. Put 1 in there, we get -1/3 minus 1/2 plus 2. If we put -2 in there, we get 8/3. Let's see, 4 over -2 would be -2 minus 4. So simplifying that, we have -1/3 minus 8/3, which is -3, minus 1/2, and then 2 plus 2 is 4, plus 4 is 8. So again, we would get 9/2. All right, example 5. Found the area bounded by the curves given. And also y equals -1, y equals 1. So we're just looking at this region right here. No need to find the bounds, because they tell us the bounds are -1 to 1 here. So our area is going to be -1 to 1, right minus left. Okay, obviously the parabola-looking shape is going to be the y squared, and e to the y will be the red one there. So it's going to be e to the y minus y squared minus 2 dy. All right, so cleaning this up, we get e to the y minus y squared plus 2. And now we can take our antiderivative, which is e to the y minus 1/3 y cubed plus 2y from -1 to 1. Putting 1 in there, we get e minus 1/3 plus 2 minus e to the -1, which I'm going to write as 1 over e, plus 1/3 minus 2. So our final answer here is going to be e minus 1 over e, and then minus 1/3, so minus 2/3, and then 2 minus -2, so 2 plus 2 is 4. And we can combine that to e minus 1 over e plus 10/3. All right, our last one here. What if the curves intersect at multiple points? So we see one here. Let me see another one here. That means we're going to do two separate integrals to do this. First, let's find our intersection points. So 3x cubed minus x squared minus 10x equals -x squared plus 2x. So 3x cubed, add x squareds both sides, they cancel out, minus 12x equals 0. Take out a 3x, we're left with x squared minus 4. So our answers are going to be 0 and plus or minus 2. So 3 intersection points. The first one's going to go from negative 2 to 0. And the second one's going to go from 0 to positive 2. All right, so our area is going to be negative 2 to 0 of top minus bottom. So in the first region here, the cubic is on top. So that's going to be 3x cubed minus x squared minus 10x minus negative x squared plus 2x. All right, so that's the first region. And then we're going to add the second region, which is going to be from 0 to 2. And in that region, the quadratic is on top. So negative x squared plus 2x minus 3x cubed minus x squared minus 10x dx. I don't want this equal sign here. Just adding that. Okay, now let's clean this up a little bit. So our area is going to be the integral from negative 2 to 0 of 3x cubed minus 12x dx plus the integral from 0 to 2 of negative 3x cubed plus 12x dx. So all I'm doing there is just combining like terms here and combining like terms here. Antiderivative, so we get 3/4 x to the 4th minus 6x squared plus negative 3/4 x to the 4th plus 6x squared. There are bounds on both. Putting in 0 would get us 0 minus, putting in negative 2 to the 4th would be 16. 16 over 4 is 4, so that'd be 12. And then times, or minus 6 times 4, so minus 24. Plus, putting 2 in over here, so 2 to the 4th is 16, times negative 3/4 is negative 12, plus 24, minus 0. So we would get negative 12, which is 12 plus 12, for an answer of 24 units. And that'll do it for our look into these 3 topics. Really, it's just one topic, though, finding area between curves. That's all. Okay, thanks again for looking into my video today, everyone, and we'll see you next time.